Hello, welcome back. This is Calc 1 by Dr. Oz. Today we're going to cover an important concept of calculus called differentials. This is an application of differentiation. Well, before we start, please don't forget to sign up to my Instagram account as well as my YouTube channel. All right, we have 4 objectives to achieve today. One is to understand the concept of a tangent line approximation. This is a very good approximation to estimate the values of functions. And second is to compare the value of the differential dy with the actual change in y. So we have dy and the actual change of the function values. So how do we sort of like relate these two things? And third, we're going to estimate a propagated error using a differential. So what is the sort of like the error that we make by using the differential? And also, we're going to find a differential of a function using the differentiation formulas. So hopefully at the end of the day, we're going to achieve 4 of these objectives. All right, the first objective is about tangent line approximations. Let me just tell you what it is exactly. Let's say like we have a differentiable function f, and it's differentiable at c. Okay. What is the equation of the tangent line to the curve of f at x equals c? Well, the point is obviously the point is like c and f of c, and we're looking for the equation of the tangent line, and we know that the equation of the tangent line is written as y minus the y coordinate equals let's say slope m times x minus c. Again, here m is the slope of the tangent line, and the slope of the tangent line is found by finding the first derivative of the function and substituting c for x. So this is the slope of the tangent line at x equals c, and at the end of the day we have y equals, well, first of all, y minus f of c equals f prime of c times x minus c. And if you add f of c to both sides of the equation, okay, so these guys cancel out, and then we get this formula here. Okay, so equation of the tangent line, if you write it as like y equals the rest, is exactly like this. So this is going to serve as a good approximation of f at point C. Okay, and then this approximation is called tangent line approximation. So essentially, we're just writing the equation of the tangent line at the given point to find a good approximation of the function at C. Okay, and obviously this is a linear approximation because we're looking at the tangent line to approximate the values of the function. Okay, so well, from this approximation we can also deduce that as x approaches c, as you see that this part here is going to converge to 0, and then the corresponding y values would converge to the function value at c. Okay, so this is also another observation that you can pass the limit, as I said, as x approaches c, and the corresponding values would approach to f of c, which is pretty much expected. Okay, so here is one example. Let's go through together. So we have the function 1 plus sine x, and we're considering the point 0, 1. Okay, so in other words, c equals 0, f of c, which is f of 0, which is 1 plus sine 0. So 0 here is radian in radian, so this is equal to 1 because sine 0 equals 0. So as you see, like f of c equals 1, so this point is in fact c and f of c. Okay, so we're going to find a tangent line approximation, and then we're going to use a table to compare the y values of the linear function with those of x, those of f of x, on an open interval containing x equals 0. So we're going to choose an interval to start with, maybe minus 0.5, plus 0.5, and first we're going to find the values of the function at certain like test values, And then we're going to use the tangent line approximation, and we're going to evaluate the function values at those points as well. So we're going to compare like how close we are to the actual values. Okay. All right. So first, well, to be able to write down the equation of the tangent line, which let me just write it again, y minus f of c equals f prime of c x minus c. In fact, the tangent line approximation is y equals f of c plus f prime of c x minus c. Okay? And c right here is 0, and f of c equals 1. So we're going to go back and then plug those here and here. So f of c is 1 plus f prime at 0 times x. Okay, so all I need is f prime at 0. So let's find that. Well, let's take the derivative of the function. Okay, so the derivative of the function is the derivative of 1 plus the derivative of sine x. And you can use the basic differentiation formula card to deduce that you have 0 plus cosine x, so that's cosine x. And we know that f prime at 0 is equal to 1, right? Here 0 is in radians, so you can even use your calculator to calculate cosine 0, and you're going to have 1. So then this formula gives you what? 1 plus 1 times x, which is x. So in other words, y equals 1 plus x is the tangent line approximation of 1 plus sine x. And now we're going to choose an interval. As I said, the interval could be like minus 0.5, x 0.5. This interval contains 0, so that's a good interval to start with. But if you want, you can expand this interval or shrink this interval, depending on what you want, depending on your taste, in fact. Okay, so once we determine the endpoints of the interval, so we choose sample points like minus 0.1, minus 0.01, and 0.01 and 0.1. And you can, in fact, increase the number of test values within this interval. And in one case, we're evaluating f of x, and in the next case, we're evaluating its tangent line approximation, which we found that to be 1 plus x. Okay, so at this moment, you can pause the video and you can use your calculator to find, let's say, to get this number. You're going to plug in negative 0.5 in here, okay, and in here. So we're going to evaluate f at negative 0.5 and negative 0.1 to get this one, and this one, and this one, and this one, and this one, okay? And then in the next step, you're just going to evaluate the tangent line approximation at negative 0.5 and on and on and on. Well, which you can find it pretty quick because this is a linear function, so the calculation is slightly easier, obviously. To get this one, you're going to plug in negative 0.5, so it's going to be 1 minus 0.5, which is 0.5. To get this one, you're going to plug in negative 0.1, so 1 minus 0.1, that's, there you go, 0.9. You don't even need a calculator to find the values in this row, okay? So once you are done with that, you can just compare the exact values to the approximated values. So let's check. If you're very close to 0, which means like I'm talking about this test value and then this test value, right? Then the exact value is 0.99, 4 zeros, and 2. Okay? And as you see, the approximated value is 0.99. That's an awesome approximation. So if you look at the error here, 0.9900002 minus 0.99, you're talking about like what? 0.000001. So 10 to the minus 7 almost. That means if you're around 0, then this is a very good approximation. And same thing here. So this is the actual value, essentially 1.00999998, and then the approximated value is 1.01. That's as well a very, very good approximation. Okay. If you're sort of like diverging away from 0, that means, let's say you're considering 0.1 and negative 0.1. So the error could be a little bit larger, obviously. But still, you see that this is the actual value of the function at -0.1, and then the approximated value is just 0.9. So if you look at the difference here with a different color, let's say 0.9002 minus 0.9, that's going to be equal to 0.0002. It's almost like at the level of 10 to the minus 4, which is not bad. Again, this depends on the amount of precision, depends on what you are dealing with. If 10 to the minus 4 is a large value for you because you're making like experiments and you're working at the micron level, this is not a good approximation. But if you're using approximation at the level of feet or even in inches, right? So this approximation is pretty good. Okay. And if you look at the endpoints of the interval, the actual value of the function at one of the endpoints is 0.521, and then the approximated value is like 0.5. The difference is still at the level of 10 to the minus 2. If you're okay with this type of error, then go with that. If you're not, obviously this approximation is not a good approximation for you, because we are using a very simple approximation, a linear approximation, to approximate the function values. There are higher order approximations which you will probably see in more advanced math courses, like quadratic, cubic type of approximations. Then you will have sort of like a better precision, even if you get a little bit far from the point. Like in this case, it's 0. Okay, so like 0.5 is very far from 0, right? So the approximation has the error at the level of like 10 to the minus 2, which could be okay, again, depending on what kind of like physics application you're dealing with. And then in the next one, have your calculator ready and try to graph these two functions. One is like 1 plus sine x, and then the approximation is y equals 1 plus x. So try to graph both in the same window, and you can see that the black graph here, which is the original function that we started with, and the blue line match perfect. Let's say for x's stuck in this neighborhood. See, like if I look at these values, you can't really distinguish blue from black or vice versa. So blue sort of like diverge away from black whenever you sort of like exceed, let's say, these points, right? If you move in this direction, well, this line goes all the way to infinity, right? But your function makes a turn here, right? So the corresponding function values differ. And the same thing here. This function makes a turn here, and then you keep going to minus infinity. So obviously, look at the level of error here. So the level of error is huge, right? So the farther you go, the bigger error you have, okay? Whereas here, as I said, you can't really distinguish one from another, so that's why the linear approximation, which is the tangent line approximation in this case, is a very good approximation to find approximated values of the function around x equals 0, okay? Around x equals 0. All right, now let's talk about the second learning objective, which is differentials. Let's start constructing this concept here on this example. So remember that the tangent line approximation that we got came with this formulation, right? It's essentially the equation of the tangent line to the graph of f at point C. So let me just zoom in here. The black is the graph of the function, right? Y equals f of x, and then the blue line here is its tangent line approximation, okay? And as you see that, around C, in a very small neighborhood of C, this approximation is a pretty good one because, again, you can't distinguish the blue line with the black curve. But whenever you get far from that, obviously you're starting to make error, right? Like, for example, this difference is really high, this difference is getting high here. So that means we're making a huge error. So then how are you going to sort of like approximate the error. Okay, so first of all, let's say like the quantity x minus c is called the change in x, and then let's say you represent it by delta x. Okay, so let's say like you start with c, okay, and then you are, let's say, delta x units far from c. So obviously the function value here, which is represented by this black dot here, and its tangent line approximation differs, right? So here f of c plus delta x is the actual value of the function, and as you see that this part here is f of c, so is this part, right? So is this part. Let me just zoom in a little bit for you to see better. Okay. So since this length here is f of c, and then this huge length here is f of c plus delta x, so the difference between these two is the actual rise of the function from c to c plus delta x. So in other words, if the run is c plus delta x minus c, which is delta x, the corresponding rise will be f of c plus delta x minus f of c, which is in fact, let me just clean this part a little bit. Hold on. In fact, let's clean everything. Okay, let me just rewrite this. Rise and run. Right? Run is c plus delta x minus c, and then the rise is f of c plus delta x minus f of c. Okay? And the difference here, so this is f of c, this is f of c plus delta x. So this part here is called in fact, it's called the run. Rise, I mean, sorry. Okay? And the tangent line approximation is in fact taking you all the way to here, right? Because it's f of c plus f of c plus f prime of c times x minus c. Well, here we call this delta x, right? So then what do we have here? Then f of c is right here, and this is the approximated value. The difference is going to be what? F prime of c delta x. Okay? So the rise, in other words, is supposed to be very close to f prime of c times delta x to get a better approximation. To get not a good approximation, then this difference, rise minus f prime of c times delta x, could be really high. Okay. So when delta x is very small, the change in y can be approximated as shown. Here we go. Rise is equal to, as I just said, right, f of c plus delta x minus f of c, and that is approximated by f prime of c delta x. So this difference here, f prime of c delta x, all right, is the approximation. Okay, an approximation of what? Delta y, which is the actual change of y, and the approximation for that is f prime of y, f prime of c times delta x. Okay, and delta x is traditionally denoted by dx, so we don't really write delta x, but for the sake of this section, let's continue with that notation. But in the future, we're gonna call it like dx, and then that's the differential that's going to be denoted by differential of x. Okay, and f prime of x delta x is denoted by dy. Okay, and it's called the differential of y. Okay, so in other words, delta x versus dx, essentially these two are the same. You will see in the future we're gonna take them equal, but delta y, which is the actual change in function value from c to c plus delta x, is approximated by dy. Okay. All right. Again, going back to here, f f of c plus delta x, if you take y to be f of c plus delta x, and this x to be c plus delta x, right? So essentially you have f of c plus delta x equals f of c plus f prime of c times delta x, and this implies what? F of c plus delta x minus f of c is f prime of c times delta x. So this actual change is in fact approximated by f prime of c times delta x. This is exactly what we're doing in this slide. Okay, and let's put this as a good definition here. Okay, so this definition says that if you have a differential function on an open interval containing x, the differential of x is any non-zero real number, that's the change in x essentially, and the corresponding change in y is denoted by f prime of x delta x. As I said, delta y is approximated by dy, okay, and dy is in fact f prime of x dx. So if you want to find a good approximation, obviously you want to make dx small so that f prime of x is going to represent f prime of x times delta x is going to be as close as possible to the actual change in y values, which is delta y. Okay? All right, let's have an example just to see the difference between delta y and dy. So let's say like we have a function y equals x squared, and the question is asking to find dy when x equals 1 and dx equals 0.01. That's the first thing. Compare this value with delta y for x equals 1 and delta x equals 0.01. So we have the y equals x squared curve. Let me just put the graph first. Okay, so this black guy here, the black curve, is y equals x squared, and you have its tangent line approximation here, right? That's a line. So when you jump from 1 to, let's say, 1.01, how do you estimate the change in y values? In other words, when the run is 0.01, what is the corresponding rise approximated by the tangent line approximation? And we're going to compare that to the actual value of the change, which is delta y, right? When again x changes from here to here. So it's a very small increment of x, and you want to see like the actual increment and the approximated increment in the function values. All right, so to find the differential of y, we need the first derivative of the function. Okay, let's find that. So f of x is equals x squared, right? This is the curve for what it does. Well, f prime of x equals 2x, okay? And we know the formula, we just mentioned that, dy equals f prime of x dx. Here we go. dy equals f prime of x dx. Okay, f prime of x is 2x. So 2x times ds is in fact dy, which is the approximation of the actual change in y values. So in this particular case, dx is 0.01, and the point we're considering is 1. Okay, so if you change x from 1 to 1.01, the approximated change in y values would be 2 times 1 times 0.01. That gives you 0.02. So this is the amount of change, approximated amount of change in the function value. Okay, and we can actually calculate this precisely by looking at delta y, which is f of 1 plus delta x, or let's just put the actual formula first, x plus delta x minus f of x. And what do we have here? F of 1 plus 0.01 minus f of 1. In other words, this is equal to f of 1.01 minus f of 1. Okay? And what is this value? And we're going to plug this back in to the function. So 1.01 squared minus 1 squared. And if you do the calculation by using your calculator, let me just write it here. Okay, let me just write this here. So you have, if you use your calculator, it's 0.0201. Okay, so this is the actual change of the function value when you jump from x equals 1 to x equals 1.01. And this is approximated by dy. Okay, dy is the approximation of this number, and the approximation is found to be 0.02. And that's not a bad approximation, right? The difference between these two numbers is like 0.0001. That's in fact 10 to the minus 4. And if you look at the graph back again, let me just clean this graph. And this is exactly what I'm talking about. This is the actual change. This delta y is the actual change from, in other words, the actual rise when you have this much of run, right? So here, this is a rise, and this is the approximated rise. Okay? All right. Here's another example for you just to practice by yourself. You can pause the video and work through this problem. And this problem is very similar to what we have just covered for a different function essentially. So you have a fourth order polynomial. The point is x equals minus 2, and this is the amount of increment, 0.01, and you want to find the actual change in function value from x equals -2 to x plus delta x, which is minus 2 plus 0.01. Okay, so you go from this point to this point, which is the difference is obviously your run, and you want to find the actual rise and approximated rise by using the tangent line approximation. Well, another cool example that you may go through when you pause the video is that the total stopping distance of a vehicle is given by this function. And here t is in feet and x is the speed in miles per hour. So you drive x miles per hour, and then t is your stopping distance. Okay. So approximate the change and percent change in total stopping distance as speed changes from x equals 25 to x equals 26 miles per hour. So imagine like you're driving with 25 miles per hour, and increasing that even 1 mile per hour will change your total stopping distance. And I have a good, in fact, visual for that. So the stopping distance when you change your speed from 25 to 26 increases, and you want to estimate how much the difference would be. Okay, and you can find the actual change because you have the function provided to you. You know how to find the actual change, and you're going to use a tangent line approximation. That means you're going to find t prime, right? T prime of x dx would be the approximated change, and you will see how much difference you will have here when you change again from 25 miles to 26 miles per hour. Okay. All right, the third learning objective is about error propagation. So let's talk about that a little bit. So what is the rationale here? So let's say like you have x representing the measured value of a variable. Okay, and let's say that x plus delta x represent the exact value. That means you make delta x error in measurement. Okay, so delta x here is the error in measurement. Let's say like you're going to use the measured value x to compute another value. Okay, let's say f of x. So the difference between f of x plus delta x and f of x is called the propagated error, because you make a measurement here for x, and then you use that x as an input to calculate something else. Okay, so that means the error that you make in the measurement propagates in another calculation. Okay, so here we go. So f of x plus delta x in this case is the exact value, and f of x is the measured value. Okay, so then the difference is going to be the propagated error or measurement error. Okay, so this is in fact, this delta x is the measurement error, the corresponding change in the value of the function is going to be called the propagated error. So measurement error causes propagated error. Okay, so a good example for that is a ball bearing. Let's say like you're trying to put a ball here, and then you're trying to measure the radius of the ball here. Let's say like you measure that as 0.7 inches. Okay. Let's say like this device has a measurement error of 0.01 inch. So in other words, this value is correct up to 0.01 inch. So the actual value, in other words, actual value of the radius of the ball should be in between. So the actual radius should be in between 0.0 plus 0.01, but should be also greater than 0.7 minus 0.01. Okay. So if you don't know exactly what the actual radius is, because this device apparently is not the best device to make a good measurement, but still, whatever you read out of that is correct up to 0.01 inch. So if you want to know the propagated error in the volume V of the ball bearing, okay? So that means first we're going to measure the radius of the ball, and we're going to use this as an input to calculate the volume of that ball. So the error in measurement is going to cause propagated error. Okay? So let's look at that. First off, the volume of a sphere is given by this formula. So V equals 4/3 pi r cubed, and r is the radius of the sphere. Okay. So what was the measured radius? The measured radius was like 0.7. Okay. And the possible error would be either like minus 0.01. It's going to be in between, in fact, minus 0.01 and 0.01. As I just mentioned here, the actual radius is in fact in between 0.701, right? And then maybe 0.699. Okay, so this is the actual radius, and here you have a possible error in the measurement. Okay, it looks to be very small, but let's see how this error is going to be propagating in calculation of the volume. Okay. All right, so to approximate the propagated error in the volume, we're going to look at the derivative of V with respect to R. Okay, so this is the function V, and then the input here for that is R. So we're going to look at dV over dr. Okay, that's our f prime of x in the formula, right? But we don't have any x, we don't have any f. Instead of f, we have v. Instead of x, we have r. So, well, you're just going to take the derivative of this by using the power rule. So 4 over 3 times pi r squared is the derivative of that, which takes you to 4 pi r squared. Okay? And our goal again is to approximate delta v, which is the actual change, and this is the approximated change. So we're going to use dV to approximate the volume. Okay, so let's see. Well, r was 0.7. The error could be plus or minus. Well, delta r. In fact, let's go delta r here. Delta r is going to be plus or minus. Okay, 0.01. Okay, so we're going to plug in this in the formula here. And what is that formula? 4 pi r squared, which is the derivative that we got here, right, times dr. Okay, so delta v, which is approximated by dv, okay, which is right here. But dv, we know that to be the derivative of v with respect to r times dr, which takes you to 4 pi r squared dr. Here we go. 4 pi r squared dr. Okay. This is also, you can take it as like dr. As I said, like dr and delta r can be taken the same. Okay. And what do we get here? Well, let me just clean this a little bit. You get, if you do this calculation by your calculator, okay, 4 pi times 0.7 squared times plus or minus 0.01 takes you this much of error. Okay. So this tells us that the volume has a propagated error of 0.06 cubic inch. So what is the meaning of that? How should we interpret this? Well, if you make this much of error in the measurement, then the propagated error in the calculation of the volume would have this much of plus or minus 6% error in the calculation. It's not percent, sorry, in the calculation of the volume. So whatever the volume you get out of this calculation would be correct up to plus or minus 0.06158 cubic inch. All right, we also want to have like a percent error. So then we're going to look at the ratio between dV and V. So this is the actual volume. This is the approximated volume, right? And the approximated volume, we just found that to be 4 pi r squared dr. And the actual volume is 4 over 3 pi r cubed. Okay, without putting any numbers in, we can just like cancel out some of the terms. So essentially, pi cancels. You have r squared and r cubed, so that's r being left in the denominator. And 4 and 4 over 3, if you flip the bottom 4 over 3, so you have 3 over 4, they cancel out. So you have 3 times dr over r in the simplification. So, well, dr now is going to be replaced by plus or minus 0.01, and r is 0.7. Here we go. The relative error, we call this relative error, is like 0.0429, and this is in fact a percent error, which is like 4.29% error you make in the calculation of volume if you make a measurement error of 0.01 inch. Okay. So we did two things here, right? We found that the volume has a propagated error of 0.06 cubic inch. This doesn't really tell us much because of the units. So to get the units out of the way, we should look at the percent error, because that's more important to us, to see the bigness of how big the error is. That's why I look at the relative error or percent error. So it's found by looking at the ratio of the approximated volume divided by the actual volume. So in this case, you have a 4.29% plus or minus error in calculating the volume of the ball. All right, so the last objective, hopefully, is going to be done here. So it's about calculating differentials. Okay, so we're going to talk about that a little bit. Okay, so let's check all out. So we had the differentiation rules, but we can put them in a differential form. Okay, for example, we took the derivative of c times a function of x, which is u in this case, and then we wrote it as like cu prime. But if you don't want to write it this way, you can use a differential notation. C times this is what we were doing before, right? c times u prime. Okay, so I can write this with the differential notation instead of putting a prime here. So I put this c times du. Okay, d of c times u is in fact c times du. Okay, and the same thing for the derivative of the sum or difference of two functions. So we had u plus or minus v prime, and if you wrote it as like u prime minus plus v prime, we can change that to the differential notation. So d of sum or the difference of two functions, u and v, is in fact du plus or minus dv. And same thing for the product rule. So you can write the product of two functions. Remember that we were using the product rule, u prime v plus u v prime. So instead, whenever you see prime, you replace that by d. d of uv equals d of u times v plus u times dv. And likewise, you can do the same thing for the quotient rule. Okay? So in this particular example, we're going to sort of like try to find the differentials of functions. So, well, first off, if you write everything in the Leibniz notation, dy dx notation, then like the differential just follows. So, for example, dy over dx is the derivative of y with respect to x. That's 2x. So dy should be equal to 2x times dx if you multiply both sides by dx, right? So these guys cancel out, dy equals 2x dx. Or you can just write it like this. So dy equals dx squared. Right? This is exactly what we're doing here. dy equals dx squared. What is dx squared? Well, 2x times dx. But again, this sort of like formulation may sort of like confuse you a little bit. So instead, write everything in dy over dx form whenever you talk about the derivative of the function. For example, in the next example, let me just go through the next example. So y equals radical x. So when I try to find the derivative of that, I'm going to use this notation here, dy over dx, and the derivative of this is just found by using the differentiation rules. So first we write this as like x to the power of 1/2 and use the power rule. Okay, so the derivative of that is 1/2 x to the power of minus 1/2, and use the reciprocal. And use the definition of x to the power of 1/2, that's radical x, so you have 1 over 2 radical x. So this part takes care of the derivative of x to the power of 1/2. And then how do you sort of like get the differential of y written in terms of differential of x? Well, you're just going to multiply both sides here by dx. Right? So when you do that, dy turns out to be 1 over 2 radical x times dx. Okay, it's like we're just using the differentiation rules. On the left, you have dy. On the right, the function differentiated times dx. So here we go. We have 2 sine x. So dy should be the derivative of 2 sine x, which is 2 cosine x times dx. So this way, in fact, you can see the relationship between dy and dx, right? So the change in x results in change in y, and then this is sort of like putting the relationship between these two. Okay. And at this moment, you can go through this example here just to practice your skills in differentiation. As you see that I have 3 functions provided to you. So why don't you go ahead and maybe pause the video and then try to find the dy here and dy here and dy here. All we're going to do here is just to use the product rule, to use the formula for taking the derivative of ln of a function in the chain rule form. That's going to be u prime over u. Okay, and then the same thing for this one. You have a formula for arctan x or arctan x minus 5 in the basic differentiation formula card. So why don't you use those to write dy in each case as y prime times dx essentially. So you're just going to find the derivative of this by using the basic differentiation rules, and and multiply that by dx, and then you will do the same thing. You will do the same thing for the others as well. Okay. All right, our final example to close this section is approximating function values to sort of like achieve one of the, in fact, the last learning objective. We just mentioned about that, but we want to sort of like reinforce that concept with an example like this. Let's say like you're trying to find the value of radical 16.5. Okay, so well, if you don't have a calculator, then probably you won't be able to write the exact value or even approximated value of this. If this was radical 16, then you would just write 4 as a result of this calculation, and you won't need a calculator at that time. So the idea here is that I want to use the differentials concept to approximate the value of radical 16.5 without using a calculator. Okay, so this is sort of like the goal of this example. Okay, so what I'm going to do here is I'm going to choose the function to start with as radical x. As you see, like there's no function specified in this problem, so you have to come up with this by yourself. Okay, because it says use differentials. To be able to use differentials, remember dy equals f prime of x dx. So I need to start with a function y equals f of x. Okay, so in this case I'm going to use the root function to start with. Okay, and as you see that f of x plus delta x is approximated by its tangent line approximation, right? We just talked about that, f of x plus f prime of x delta x. Okay, and f prime of x, since I just mentioned in the previous slide, so this is x to the power of 1/2, and if you take the derivative of that, right, so here we go, let me just bring that back here. So if you take the derivative of that is 1/2 radical x, so dy is in fact equal to dx over 2 radical x. So let's just use this right here. So this is the derivative of root x, and you multiply it by dx. So in fact, this part is dy, right? All right. And so now the question is, how am I going to choose x and delta x? Okay. So, well, we're going to choose x to be exactly equal to 4. Or not, sorry. This is going to be wrong, right? X is going to be 16, right? Because 16 is something that I need the root for. I know the root of it, which is 4, right? And the delta x here, or dx, is going to be 0.5. So in other words, f of 16 plus 0.5, who is this guy here? Well, this is radical 16.5, which is what I'm after. It is going to be approximated by something that I know how to calculate without using a calculator. In fact, this is equal to f of 16 plus 1/2 times root 16 times delta x, and I know delta x, right? There we go. What is f of 16? Well, f of x is radical x, so this is radical 16 plus 1/2 radical 16 times 0.5. Okay. And what is radical 16? That's 4, so this is 4. And this is also 4. Right? So what do we get here? So 4 plus 1/8 times 0.5. Right? So it's 1/16. Okay? And this is approximately equal to 4.0625. You can also leave it like this. 4 plus 1/16 is the approximation that you can use, right, of what of the root of 16.5. Okay. There we go. So in other words, Radical 16.5 has a good approximation, which is 4.625. All right. You can actually see it from the graph of radical x. So go ahead and use your calculator to graph radical x. Let's say for x min to be 0, x max to be 20. Okay. And you can actually go ahead and then check the tangent line approximation of this function radical x. So you essentially look at this tangent line here, and that turns out to be, that turns out to be 1 over 8x plus 2. Okay. As you see that whenever you are around 16, right, you can't really distinguish these two graphs. Let me just clean this to see that the blue line cannot be distinguished from the black curve here. Okay, so that's why this approximation is a very good approximation. So radical 16.5 can be approximated as 4.0625, and you don't need a calculator here. You can even leave the result right here, 4 plus 1 over 16. All right, a good exercise for you to work on right now. You can pause the video, but try to sort of like approximate cubic root of 26 by using the idea that we just talked about. So then you're going to look at three things. You're going to tell me what f of x is. You're going to tell me what x is, and then we're going to tell me what dx is. And then the sort of like the calculations are pretty similar. You can mimic the calculations in this example. Okay, so but I'm going to leave this as an exercise and play with this, and I'm not going to show you the solution. So this is an exercise for you. Please work through that. But this would probably give you an idea about like what x could be, because let me just give you a hint here before I finish this video. So if this number was 27, you would be able to find the cubic root of 27 without a problem, because cubic root of 27 is 3. So that could be your starting point. All right, so today we discussed about differentials, and we had 4 learning objectives to achieve. We first found a good tangent line approximation to a given function, and we were sort of like able to compare the approximated change of the values of the function versus the actual change of the values of the function at a point x. And we also talked about a propagated error using a differential, and you make a measurement error, and then that propagates because you use that measured quantity to calculate something else. So we had a good example for that, and eventually we were able to find differential of a function using differentiation formulas, and eventually we ended up having a good example to find the cubic root of 26. So how do you approximate the cubic root of 26 by using differentials? All right. Okay, this is the end of the video. I'll see you in another video. Bye.